So with implicit differentiation under our belt, now we are going to apply this technique to help us find the derivatives of the inverse trigonometric functions. So when we begin talking about the inverse trig functions, some of you need to probably do a little review of those functions. You need to understand how they are created, know their domains and ranges, what their graphs look like, and how to evaluate these functions. The main three functions, inverse functions, that I'm going to be dealing with, that we'll be using extensively, are the inverse sine, inverse cosine, and inverse tangent, or arcsine, arccosine, and arctangent functions. Our textbook has a review of those functions in the very beginning, first chapter there. You can also, find many of the sites that I've shared where you can get reviews of those functions. Okay, with that, let's start. Let's talk about the derivative of the inverse sine function or arcsine function. Now, hopefully you remember when you see this notation here, there's an exception here. This -1 is not an exponent. So this thing here is not equal to 1 divided by sine of x. This is not the reciprocal of the sine function. That function we call what? Cosecant. All right, the cosecant function. Now, talking about the cosecant function, that -1 superscript is a indication we're talking about the inverse sine function. Okay, it's the function that, if you will, undoes the sine function. So for instance, if sine of pi over 6 is equal to 1/2, then the inverse sine of 1/2 is equal to pi over 6. Okay? So the other notation, of course, is the arcsine function. And the idea is if you think about the unit circle, that central angle in the unit circle in radians is equal to the arc length that it subtends. And so we sometimes call this the arcsine function, getting back to the original arc length or angle. Okay, so we're going to find the derivative of this function, okay, using implicit differentiation. The domain of the inverse sine function is -1 to 1. Notice that's the same as the range of the sine function. Remember, the sine function bounces between -1 and 1 as outputs. And that's, of course, remember how inverses functions work. The range of our function is equal to the domain of the inverse function. The range of the inverse sine function is -pi halves to pi halves. Now, when you think about the range of the inverse function, that should be the same as the domain of the function. The domain of the sine function is all real numbers, right? I mean, the sine function, if you remember, just goes up and down forever for all real numbers. However, to talk about an inverse, remember, the function we have must be 1 to 1. And if you think about the sine function, it's not 1 to 1, meaning for every input there's not a unique output. All right, for instance, I know sine of pi over 2 is equal to 1, but so is sine of 5 pi over 2. All right, if I go 2 pi more, around the unit circle, go all the way around the unit circle. All right. And that continues forever, right? We continually hit 1 an infinite number of times. So we need to restrict the sine function's domain, and the way we restrict it is on the interval from -pi over 2 to pi over 2. On that interval, the sine function is 1 to 1 and obtains all its values from -1 to 1. Sine of -pi over 2 is -1, sine of pi over 2 is +1. Okay, so with those restrictions, then we have the domain of our inverse sine function, -1 to 1, and the range of our inverse sine function, -pi over 2 to pi over 2. Here's the graph of the inverse sine function. So notice, as we said, it's going from, its range is going from what, -pi over 2. So right down here, about -1.57 is -pi over 2. And then up here, this is pi over 2. So this point up here is the point 1 comma pi over 2. So here's the graph, and notice the domain is just between -1 and 1, and this is the graph of the inverse sine function. So when we talk about it in terms of calculus, then at any point, what can you tell me about the derivative of the inverse sine function? What can you observe just by looking at the graph? Remember, the derivative is the slope of the tangent line. So if I pick an arbitrary point, let's say right here on the graph, what's that tangent line going to look like? We're just going to touch right at that point, right? The bottom of the ruler now is our tangent line. What can you tell me about that line? And one thing you can tell me is the slope is positive. And in fact, that will be true if you pick any other point on this curve, right? Just about, the slope is going to be some positive number, right? It's not the same positive number, but it's always positive, okay? Now we do have issues at the endpoints, right? But for any point in between -1 and 1, we're expecting the derivative to be positive. Okay, so let's go ahead and derive this. So let's let y be the function sine inverse of x. Okay, so notice right away, and we see the restriction on y, and this is going to be important, that y, the output, the range value, right, is between what two values? -pi/2 and pi/2. X is between -1 and 1, but y here is between -pi/2 and pi/2. And that's going to be important. Okay, now y is equal to the inverse sine of x if and only if sine of y equals x. So what I'm doing here is applying the inverse function property. All right? If I plug y into the sine function and I get an output of x, then if I plug x into the inverse sine function, my output's going to be back to y. They cancel each other out. Right? And what do we want? We want, in this case, the derivative of the sine inverse function, which is dy dx. Okay. So how do we proceed? We're going to proceed by implicit differentiation. Take the derivative with respect to x of both sides of this equation that we have. Now the right hand side is pretty darn easy, right? What's the derivative with respect to x of x? That's just 1. That's not a problem. Over here, what do we have? Derivative with respect to x. It's not sine of x, it's sine of y. And what do we know about y? Y is a function of x. And we do know what y is as a function of x. Y is sine inverse of x. But we don't know its derivative yet. But indeed, y is a differentiable function of x. And so we are going to use the chain rule here since I want the derivative with respect to x. The inner function is y, and the outer function is sine of y, right? Sine is the outer function, y is the inner function. So chain rule says what? Derivative of sine is cosine, evaluate the inner function y, times the derivative of the inner function, which indeed is dy dx. So this is going by, right, the chain rule. Okay, so cosine y, dy dx. There it is. We want dy dx. There it is. I found it. Can we solve for it? Yeah, I need to divide by cosine of y. I get 1 divided by cosine of y. There's my derivative. Now, as we've seen when we were doing implicit differentiation, our derivative, all right, y is a function of x, we find the derivative, and notice it involves the variable y. We typically like to see it in terms of x only. Okay? If we can get it in terms of x, we really would want to do that. And so, can we do that? Yes. Here's the thing. I want cosine y to be expressed as something in terms of x. Can I do that? Well, let's look up here. Notice I do know that sine of y is equal to x. Right? Got cosine y here, but this is sine of y. If I wish there was some way to relate cosine y to sine of y. If I could say cosine y is somehow related to sine of y, then I can get it related to this variable x. Is there a way to do that? Yes, there is a way to do that. And it's by a very important identity that you should all be familiar with. All right, the Pythagorean identity. And what's that say? It says that sine squared y plus cosine squared y is 1. Okay, this relates these two functions, sine and cosine, together. And what I want to do is I want to find cosine y in terms of sine. So I'm going to solve for cosine y. So first of all, I'm going to subtract sine squared y from both sides. Now this is cosine squared y, or cosine of y squared. So how do I undo the squaring? I take the square root. Now, when I do, however, what do I have to do? I've got both the positive and negative square root of 1 minus sine squared y, right? I have to take both the positive and negative root. Well, that's, here's cosine y in terms of sine of y, but sine of y is in terms of x, so I can replace that with x, right? But the problem is plus or minus. I can't have plus or minus here. This is a function. I want the derivative as a function of x. And if there's a plus or minus, that's problematic, because that means for any given input x, there will be two possible outputs. We can't have that. So that's problematic. But we have a resolution. Remember at the very beginning what we said about y. Y is between negative pi over 2 and pi over 2. And that's real important. Think about what that means for the value of cosine y. If y is between negative pi over 2 and pi over 2. Think about that unit circle. If you go back to the unit circle, it kind of helps us out a little bit visualizing this. All right? Y is the angle in here now is really what we're talking about y is, so be careful. It's not the y coordinate here. But y going from what? Negative pi over 2 to pi over 2. Right, negative 90 degrees to positive 90. So we're talking about angles in the first and second quadrant. And what do you know about cosine on this interval? What do you know about cosine in this interval? Over this interval, cosine y, right, is positive. Cosine is positive in the first and fourth quadrant, negative back here. So that's important. Since cosine is positive, I know that this has to be, in this case, for my situation, positive. Can't be negative, because we have restricted y between negative pi halves and pi halves, where the cosine function is positive. And so with that, right, I can now replace cosine y with positive square root of 1 minus sine squared y. But since sine of y is equal to x, right, then we can just say this thing is equal to 1 over what? Square root of 1 minus x squared. And there's my answer for the derivative of the, what? Inverse sine function in terms of x only. So here's a new rule that we have. Okay. So, what I would like you to do is to similarly prove the derivative of the inverse cosine function. And it's going to look pretty familiar here. The derivative of the inverse cosine function, or the arccosine function, is negative. There's a negative sign there. Negative 1 divided by the square root of 1 minus x squared. Derivative of sine inverse is this. Derivative of cosine inverse is negative 1. So they're very similar, just one's positive, one's negative. And you can prove it the same way we did above, up here. And of course, you might remember the derivative of sine of x is cosine of x, but the derivative of cosine of x is negative sine of x, and that's essentially what's going to make that negative. So you prove that for homework. We have this one and this one. I want to do the one for tangent x now, inverse tangent x, that is. So let's take a look at that. Let's find the derivative of the inverse tangent or arctangent function. Now, the domain of the inverse tangent function is all real numbers. And that's because the range of the tangent function, if you remember, was all real numbers. The tangent function, right, had vertical asymptotes at pi over 2, negative pi over 2, and so on. I mean, the graph of the inverse tangent function, if you remember, looks something like this. Where it was, the graph of the tangent function, excuse me, looks like this. And that just repeats forever. In fact, it has a period of pi, if you remember. Okay? But when we do the inverse tangent function, then these vertical asymptotes basically become horizontal asymptotes. Our domain for the inverse tangent function is the same as the range for the tangent, all real numbers, but its range is between negative pi over 2 and pi over 2. And that's because these vertical asymptotes were at x equal negative pi over 2 and pi over 2. We restrict the tangent function just on that interval so that it's 1 to 1, and we can talk about its inverse, and therefore those become horizontal asymptotes for the inverse tangent function. And we talked about this function when we were doing limits at infinity as well, if you remember. So this is y equals pi over 2, and this horizontal asymptote down here y equal negative pi over 2. Alright, so we're going to proceed the same way. We'll start with the fact that y is the tangent inverse function, or arctangent function, and that's true if and only if what? If and only if tangent of y is x. That's the inverse relationship. And now take the derivative with respect to x. Both sides of this equation. Okay. This one's pretty easy over here. The derivative with respect to x is just going to be 1. What about here? Derivative with respect to x of tangent y? That's chain rule, right? Outer function tangent, inner function y. So the derivative of the outer function, what's the derivative of the tangent function? Who remembers that? Derivative of tangent is secant squared evaluated at y times the derivative of the inner function. Derivative of y with respect to x is dy dx. That's what we're looking for. Solve for dy dx by dividing by secant squared y. There's my derivative. Again, though, it's in terms of only y. I would like it to be in terms of x. So is there a way to get that? I know that tangent y is x, but what about secant squared y? Well, again, we are going to go to the Pythagorean theorem. And this time, can't spell Pythagorean theorem. There's actually 3 different Pythagorean theorems, if you will, 3 different equations, 3 different identities. I said theorem, it should be identity, excuse me. No. Identity is what I meant. And we saw the one here, right? Sine squared y plus cosine squared y is 1. But you can get the one I'm going to use if you divide both sides of this equation by cosine squared y. You get sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared y is secant squared. And so you should recall this one, which is tangent squared y plus 1 equals secant squared y. So that is true. And so with that, I can simply write this as being equal to what? What is secant squared y? Tangent squared y plus 1. But tangent y is x. Right? Tangent y is x. And so that allows me then to say that dy dx is 1 divided by x squared plus 1. And in fact, there's our rule then. We can say that the derivative with respect to x of the inverse tangent function is 1 divided by x squared plus 1. Okay. So we basically have 3 new rules, one for the inverse sine's derivative and inverse tangent, and then hopefully you'll derive the one I showed you above for the inverse cosine. There are 3 more inverse trig functions, the inverse cotangent, inverse secant, and inverse cosecant. It can be shown that their respective derivatives are as follows. Okay. Right. See the derivative of the inverse cotangent function, very similar to the derivative of the inverse tangent function with just a negative 1 there. As far as I'm concerned, the ones I'm going to hold you to are these 3 up here. You need to know these 3. These down here you won't have to know if you are needing them on something. I would give those forms to you. And also I would say that the forms for the inverse secant and inverse cosecant, they can actually vary because the way it depends on how you define the inverse secant and inverse cosecant functions. There's different ways to restrict the domain of secant and cosecant to define their inverse functions, and so the derivatives can look slightly different. These have absolute value involved in them. There's other ones that do not have that. So it just depends on the situation. But again, the top 3 you do have to be able to be familiar with. And keep in mind, again, as I say, we use the -1 superscript notation for the inverse sine function. You can also call it the arcsine function. Okay, so that's an introduction to those rules. What we'll do in the next video is we'll apply it, right? Now that we have new rules, what do? We throw them in the bucket with what? The constant rule, constant multiple rule, sum difference rule, power rule, product rule, quotient rule, rule for e to the x, rules for all the trig functions, chain rule, right? And now we have these rules to throw into the mix.